Now that we've gone over the basic calculations for a standard normal distribution and seen some examples by using the table, we want to look at some applications now of the normal distribution. So let's take a look at problem 17. The magnitude of earthquakes since 1900 that measure 0.1 or higher on the Richter scale in California is approximately normally distributed with a mean of 6.2 and a standard deviation of 0.5. According to data obtained from the U.S. Geological Survey. Okay, let the random variable x represent the magnitude of an earthquake since 1900 in California. All right, so the shape of the histogram is approximately bell-shaped and symmetric, and we're going to do some probability calculations here. So part A, what is the probability that a randomly selected earthquake in California has a magnitude of 6.0 or higher? All right. X represents the magnitude of an earthquake in California since 1900. So I want to find the probability that the earthquake magnitude, X, is 6 or more, means that X is greater than or equal to 6. Remember, equal signs don't matter if you have a normal random variable, so I'll go ahead and lose that on the next line here. Remember also, the first thing is you want to change the variable from X to Z. So I'm doing that using the formula for a z-score. Take x minus mu over sigma, and then on the other side do the same thing, only use the actual numbers. X is 6 minus the mean is 6.2. The standard deviation is 0.5, so we're dividing by 0.5. 6 minus 6.2 divided by 0.5 is negative 0.40. Okay, x minus mu over sigma, that's what we're calling z. So now we have changed the variable. And of course, in this calculation, I'm describing area to the right. Table only gives area to the left, so we would need to use the complement rule next. Take 1 minus the probability that z less than or equal to negative 0.4 to get this area to the right. Okay. Again, I did not need the equal sign. Still make sure that you switch the sign, though, because you're referring to area to the left now. And if you go to the table and look up that area to the left, here's negative 0.40. The area to the left of negative 0.40 is 0.3446. Subtract that number from 1 and you get 0.6554 is the answer. Okay, so now what that means to us is if we were to look at all the earthquakes that have ever happened in California going back to 1900, and we were going to randomly select one of them, there is a 65.54% chance that the magnitude of that earthquake would be 6 or higher on the Richter scale. Part B, what is the probability that a randomly selected earthquake in California has a magnitude less than 6.4? All right. So we want to find the probability that an earthquake magnitude, which we're calling x, is less than 6.4. Change the variable from x to z using the formula for a z-score. Take x minus mu over sigma, and then use the actual numbers on the other side. 6.4 minus 6.2 divided by 0.5. That is 0.4. And so now I'm looking at the probability that z less than 0.4. Okay, now in this problem, we're describing area to the left. Of course, I could have known that, very early on in the problem that we're talking about area to the left, so I don't need a complement rule like I used up here. I can go right to the chart and get that area to the left. Let's do that now. So I need to go to 0.40 in the chart. That area to the left of 0.40 is 0.6554. And so that would be my answer. Okay, and the interpretation then would be to say that if we were to look at all the earthquakes that have ever happened in California going back to 1900 and we randomly select one of them, there is a 65.54% chance that the magnitude of that earthquake would be some number less than 6.4 on the Richter scale. Now, if you compare this number to what we had in part A, they are the exact same number, okay, and why that happened is because of the symmetry of the bell curve. So here I've drawn a picture. I've got this random variable x. X represents the magnitude of an earthquake. So I've got all these values that would go on the x-axis. Of course, the mean goes at the center. The mean is 6.2. And in the first calculation, we wanted to find the probability of selecting an earthquake that had a magnitude that is 6 or more. Okay, so I would shade that area to the right of 6, and that shaded area is 0.6554. Now in part B, I wanted to find the probability of selecting a magnitude that was less than 6.4. Okay, so here's 6.4. Now 6 is 0.2 units away from 6.2. 6.4 is also 0.2 units away from 6.2. We're describing the area to the left of 6.4, and that number was also 0.6554. Because 6 and 6.4 are the exact same distance away from 6.2, the area to the right of 6 and the area to the left of 6.4 are going to be exactly the same number here in this problem. So it's by the symmetry of the bell curve why those numbers ended up being exactly the same. Part C, what is the probability that a randomly selected earthquake in California has a magnitude between 5.8 and 7.1? All right, so I've got that written down here. X is the magnitude of an earthquake. I want that number to be between 5.8 and 7.1. And again, I've got to change the variable from x to z. So in the middle, I'm going to want x minus mu over sigma, and do the same on the left side and the right side, only use the actual numbers. 5.8 minus the mean is 6.2 divided by the standard deviation, that's 0.5. That left z-score ends up being negative 0.8. And then on the right, x is 7.1 minus the mean is 6.2 divided by the standard deviation, which is 0.5. That number, when you simplify, is 1.8. So now I'm in z mode, right? And now I can compute the area between these two z-scores. Now we've seen problems like this before. To find the area between two z-scores, you take the area to the left of the larger z-score minus the area to the left of the smaller z-score. Since you're removing the unwanted space, that is the area to the left of the smaller z-score, you'll have what's left over, which would be the area between these two numbers. That's what we want. Both these signs are less than signs. That's what I want because I'm describing area to the left on each one of them. Okay, the probability of being less than 1.8, if we go to the chart, here's 1.80. That area to the left is 0.9641. Okay, and that's what I got there. And then the probability of being less than negative 0.8, or negative 0.80, that area is 0.2119. Okay, subtract those two areas, and we get 0.7522 as the answer. Now, what that means to us is that if we were to look at all the earthquakes that have ever happened in California, going back to 1900, and randomly select one of them, we have a 75.22% chance that the magnitude would be some number between 5.8 and 7.1 on the Richter scale. Now, here's just an observation. Notice how 6.2 is between those two numbers. 6.2 is the mean, and the bulk of the information is going to be around the mean. So in this problem here, like, it's not surprising that we had a fairly high probability since we're looking at most of the earthquakes that would ever occur, you know, and their magnitudes being around the mean. Part D, the Great San Francisco earthquake of 1906 had a magnitude of 8.25. Is an earthquake of this magnitude or higher unusual in California? Okay, well, let's find the probability that an earthquake magnitude, x, would be 8.25 or higher, means that x is greater than or equal to 8.25. And then based on our answer, we can then say whether this would be unusual. Change the variable from x to z. And the z-score here is 4.1. Okay, now I want the area to the right of 4.1, so I want to use the complement rule on the next line, flip the sign there. 1 minus the probability that z less than 4.1. Okay, if I go to the chart now, notice how 4.1 is not available to me, okay, on this chart. The biggest z-score is 3.49, but I hope that by this point you've kind of got an idea of how the chart works. Okay, the smallest z-score is negative 3.49 on this chart. The biggest one is 3.49 on this chart. Now the areas are increasing as you read the chart top to bottom. Okay, so notice how we've got, we're very close to 0 here to start, and the numbers increase, and we're getting to an area that is very close to 1. Okay, now probability can't be bigger than 1, so of course we're not going to go beyond that number, but that's where we're headed towards. 4.1 is not available, but I know where I'm headed towards. Okay, the area to the left of 3.49 is 0.9998. So the area to the left of 4.1 is going to be bigger than that, but still less than 1. Okay, it'd be like maybe 0.99998 or 0.99999, something like that. For all practical purposes, that number is very close to 1, with it being 0.99998, so let's just call it 1. Use the approximation sign since I'm not using the exact number here. It's 0.999, something bigger than 0.9998. 1 minus 1 is 0. So was this unusual? Yeah, this is very unusual because the chances of an earthquake magnitude like this happening is practically 0. Like, this was a big deal. That's why they called it the Great San Francisco Earthquake. It did a lot of damage. It's a very powerful magnitude. And we just don't see earthquakes of that magnitude occurring a lot. And so, there's roughly a 0% chance that would that you'd be selecting a number that high, if it were a random thing. Part E, what is the percentile rank of a California earthquake that measures 6.8 on the Richter scale? Okay, remember percentile ranks going back to chapter 3. A kth percentile rank is a number such that k% of the data is less than or equal to that number. Okay, so now in this question, I could also ask what percent of earthquakes are less than or equal to 6.8? Okay, or what is the probability of selecting an earthquake magnitude that is less than 6.8? Once we have that probability, we can then convert that number over to a percent and know what the percentile rank would be. So let's go ahead and do that now. I want to find the probability of selecting an earthquake that has a magnitude that is less than 6.8 on the Richter scale. Change the variable using the formula for a z-score, and that z-score is 1.20. So the probability that z less than 1.20, that's we're describing area to the left, and we can go to the chart and look up that number here. 1.20, the area to the left is 0.8849. Okay, and that's what I have written. Now, remember that a percentile rank is going to be a whole number value there, and so round as you normally would. We'd be in the 88th percentile rank. Okay, so 88% of earthquakes are going to be less than or equal to 6.8 on the Richter scale would be the interpretation there. Part F is a similar deal. It says, what is the percentile rank of a California earthquake that measures 5.1 on the Richter scale? Okay, or you could also ask, what percent of earthquakes are less than or equal to 5.1 on the Richter scale? Okay, or what is the probability of selecting an earthquake magnitude that is less than 5.1? Once we have that probability, we can then convert that to a percent and know what the percentile rank is. Let's do that now. Okay, so I'll change the variable here from x to z, and the z-score that I'm getting is negative 2.20. We're again describing area to the left. Less than or equal to is really keywords to describe area to the left. That's why I've got a less than sign set up on both of these. And because this is area to the left, I can go to the chart now and look up that area. The area to the left of negative 2.20 is right here, 0.0139. Okay, and so this would be in the first percentile rank. And now we were talking about how the Great San Francisco Earthquake was a very unusual thing. We just don't see earthquakes of that magnitude occurring. On the other hand, if an earthquake happened in California and it measured 5.1 on the Richter scale, like that would also be unusual, because only 1% of the data is less than 5.1 on the Richter scale. Okay, so we don't see very weak magnitudes occurring, more specifically numbers that are less than 5.1 on the Richter scale, that just doesn't happen much at all either. Okay. We'll stop right there.